Summer's coming, and if you own a pool, you already know what that means. The first few weeks are perfect. The water is cool, exactly where you want it. Every afternoon swim feels like exactly what a pool is supposed to feel like. Then July arrives. The air temperature climbs past 90. The sun is direct and relentless. Slowly, day by day, your pool stops being a place you escape to. It starts being a place that disappoints you. You walk out expecting relief. You step into water that feels like a warm bath. You wait for that cooling sensation. The whole point of having a pool is supposed to provide, and it never comes. The water is 88 degrees, maybe 90, the same temperature as the air. You start thinking about what it would cost to install a pool chiller, or whether running the pump at different hours might help, or if the pool store has something. What nobody tells you before that first brutal July, what nobody in the pool industry has any financial reason to tell you, is that there is a way to keep pool water genuinely cool through the hottest weeks of summer. It costs less than $1 to set up, requires no electricity, no installation, no chemicals, and no ongoing cost of any kind. The physics behind it is older than the concept of a swimming pool. It is older than the concept of a backyard. It is the same natural cooling mechanism. Ancient civilizations used to manage water temperature in some of the hottest inhabited regions on Earth, preserved across thousands of years through simple observation and practical necessity, then quietly replaced in the modern era by powered systems that require a monthly energy bill. So before summer arrives and your pool turns into a bathtub, understand this. This is the story of how water actually heats and cools, why your pool behaves the way it does, and why the solution has been sitting in plain sight the entire time. To understand why this matters and why the solution works, you need to start with the physics. How a pool gains heat, because most pool owners have a vague understanding. They've never thought carefully about the specific mechanisms involved or how they can be interrupted. A swimming pool is, from a thermodynamic standpoint, a large open collector of solar radiation. The water surface is exposed directly to sunlight across its entire area for most of the daylight hours. When solar radiation strikes a water surface, a portion is reflected back into the atmosphere, and a portion is absorbed. Liquid water is actually quite effective at absorbing solar radiation, particularly in the infrared portion of the spectrum. The energy that is absorbed is converted to heat, raising the temperature of the water molecules at and near the surface. That warm surface water then mixes with the cooler water below through convection and circulation, gradually raising the temperature of the entire pool volume over the course of the day. The mathematics of this process are worth thinking through because they reveal how significant the solar heat input is. A typical residential swimming pool holds somewhere between 15,000 and 30,000 gallons of water. That is an enormous thermal mass, meaning it takes a lot of energy to raise the temperature. And yet pool water temperatures regularly climb to 85, 90, even 95 degrees Fahrenheit. In regions with strong summer sun, sometimes within a single week of warm, clear weather, the sun is delivering that much energy to your pool surface continuously across every hour of direct sunlight exposure. On a clear summer day in a southern climate, the solar energy striking a pool surface can be equivalent to running a very large electric heater in the water continuously for the entire day. The numbers are staggering when you calculate them, and they explain why electric pool chillers are energy intensive, which have to actively pump heat out of that enormous water volume against the continuous input of solar energy. Are energy intensive and expensive to operate. You're fighting an enormous and continuous energy source with electricity, which is exactly as costly as it sounds. But here's what the pool industry does not lead with. In their marketing for chiller systems, the solar energy input is not invisible or unstoppable. It can be blocked. It can be reflected before it ever reaches the water surface, and the cost of blocking it is essentially nothing compared to the cost of removing it, after it has already been absorbed. This is the fundamental insight that separates the ancient approach from the modern commercial one. The ancient approach worked with the physics upstream, preventing heat from entering the system. The modern commercial approach works downstream, removing heat after it has already been absorbed, which is always more energetically expensive than prevention. A reflective cover that blocks 70% of the solar radiation reaching your pool surface eliminates 70% of the daily heat input before it ever enters the water. An electric chiller has to do the thermodynamic work of removing that heat after the fact. Fighting against continuous solar input while it does so, prevention is almost always cheaper than remediation. And in thermodynamics, that principle is absolute. Understanding where this knowledge came from requires going back much further than the history of swimming pools. A surprisingly recent leisure concept. Water temperature management using shade, structure, and airflow has been practiced for thousands of years across multiple civilizations. All arrived at the same fundamental principles independently because the physics is universal and the problem was urgent. In the ancient Middle East and North Africa, water was not primarily recreational. It was a survival resource. Keeping it cool in environments where ambient temperatures regularly exceeded 100 degrees Fahrenheit was a matter of life and death. Communities with cool water had supplies safe to drink for longer, more palatable, and consumed in adequate quantities during extreme heat. It also retained useful properties for irrigation and food preparation. Communities that allowed their water to heat in exposed reservoirs faced spoilage, algae growth, and reduced palatability. This had real consequences for health and agricultural productivity. The solution that emerged across these civilizations was not arrived at through formal scientific analysis. It was arrived at through observation and accumulated practical experience. Water that was shaded stayed cooler. Water exposed to moving air cooled faster in the evening. It lost less total heat overnight before the next day's solar input began. Water stored in deep structures, whether wells, cisterns, or underground chambers, stayed at temperatures far below ambient air. The surrounding earth insulated it from the extremes of the surface environment. The ancient Persian civilization developed the yakchal, an above-ground insulated structure for storing ice and chilled water. This was in a desert environment where summer temperatures were brutal. The design incorporated thick mud brick walls with high thermal mass, a shaded interior, and ventilation openings. These encouraged evaporative cooling of the water stored inside. These structures maintained temperatures cool enough to preserve ice from winter months through the height of summer. This was in environments where refrigeration would not exist for another 2,000 years. The engineering was sophisticated, deliberate, and deeply informed by an accurate practical understanding of thermodynamic principles. These principles would not be formally described in scientific language for many centuries. In ancient India, the stepwell tradition produced some of the most remarkable water management structures ever built. They combined deep access to groundwater with architectural features that maintained water temperature and quality. This was across extreme seasonal variation. The great stepwells of Rajasthan and Gujarat, some still intact today, were built to reach water at depths. Here, the surrounding earth maintained a relatively constant, cool temperature year-round. The multi-story galleries surrounding the water served not just as access architecture, but as shade structures, limiting direct solar exposure to the water surface and creating a cool microclimate within the stepwell. This made the water noticeably cooler than open surface water nearby. The women who collected water daily understood without formal education that deeper was cooler and shaded was better. The communities that built the stepwells incorporated both principles deliberately into their design. The same physical understanding that keeps a glass of water cooler in the shade than in direct sunlight was applied at architectural scale. This served communities of thousands. Across the Mediterranean world, Roman engineering produced an extensive network of aqueducts, cisterns, and distribution infrastructure. This incorporated temperature management as a design consideration. Roman cisterns were typically covered structures, sometimes vaulted with thick masonry, that minimized direct solar heating of stored water. The famous cooling properties of Roman fountains in public spaces were not incidental. The movement of water through the fountain mechanism exposed it to evaporative cooling. This is the same principle that makes standing near a fountain feel cooler than standing in still air nearby. Roman engineering texts describe the selection of shaded, north-facing locations for water storage structures as standard practice, specifically to minimize solar heat gain. These were not arbitrary aesthetic preferences. They were thermodynamically informed building decisions. They reflected a sophisticated practical understanding of how solar exposure affected water temperature. The evaporative cooling dimension of this history is equally important and deserves its own careful examination, because it is the second half of the passive cooling equation that the ancient traditions understood, and that modern pool owners rarely think about deliberately. Evaporation is a phase change process, meaning it involves the conversion of water from liquid to gas. That conversion requires energy, specifically the latent heat of vaporization, which for water is unusually high. When a water molecule at the surface of a pool gains enough energy to escape into the vapor phase and leave the liquid, it carries that latent heat energy with it into the atmosphere. The water remaining behind is slightly cooler as a result. This is why sweating cools your body, why a wet cloth on your forehead provides relief from fever, and why standing at the edge of a waterfall feels dramatically cooler than standing in still air at the same temperature. The evaporation of water is an extremely effective heat removal mechanism, and it operates entirely passively, driven by the vapor pressure difference between the water surface and the surrounding air, with no energy input required beyond ambient conditions. For a swimming pool, evaporation is simultaneously a significant source of water loss and the primary natural cooling mechanism operating on the water after sundown. During the night, when solar input has stopped and ambient temperatures have dropped, evaporation from the pool surface removes heat that was absorbed during the day and gradually lowers the water temperature. The rate of evaporative cooling depends on several environmental variables, most critically the humidity of the surrounding air and the wind speed across the water surface. Dry air can accept more water vapor than humid air, so evaporative cooling is most effective in arid climates and least effective in humid ones. Moving air carries water vapor away from the pool surface and replaces it with drier air, maintaining the vapor pressure gradient that drives continued evaporation. This is why a gentle breeze across a pool surface at night feels refreshing. and why pools in areas with consistent nighttime breezes maintain lower temperatures. Understanding these two mechanisms, solar heat gain during the day and evaporative heat loss at night, makes the entire passive cooling strategy immediately logical. If you want to keep a pool cool through summer, you want to minimize solar heat input during the day and maximize evaporative heat loss at night. Those two objectives are not in conflict. In fact, they are perfectly complementary. And achieving both simultaneously requires nothing more sophisticated than controlling what covers the pool surface and when. During peak sunlight hours, covering the pool with a reflective or light-colored material blocks solar radiation before it reaches the water. The reflective surface bounces incoming solar energy back into the atmosphere, rather than allowing it to be absorbed by the water. After sunset, removing the cover entirely exposes the water surface to the night air, maximizing the evaporative cooling that will gradually bring the water temperature down overnight. This is the entire passive cooling strategy in its simplest form. Cover during the day to block heat gain, uncover at night to allow heat release. The cost of implementing it is the cost of whatever covering material you use, which can be as simple and inexpensive as a light-colored tarp from a hardware store, or even a DIY assembly of PVC pipe and reflective foil that can be constructed for under $2 from materials available at any hardware store. The ongoing operating cost is zero. The electricity consumption is zero. The maintenance requirement is the 60 seconds it takes to pull the cover on or off. The specific details of implementation matter for maximizing the effect, and understanding them allows you to optimize the system for your specific pool and climate conditions. The single most important variable is the reflectivity of the covering material. A white or silver surface reflects far more solar radiation than a dark-colored surface. A standard dark blue pool cover, which is common and widely sold, actually absorbs significant solar energy and can heat the water beneath it rather than protecting it. This is not a design flaw for pools that need to be warmed in cool climates. It is a feature. But for pools in hot climates where the objective is cooling, a dark cover is counterproductive. The covering material should be as reflective as possible, ideally a metallicized surface or a bright white material that reflects rather than absorbs incoming solar radiation. The geometry of the cover matters as well. A cover that lies directly on the water surface minimizes the air gap between the cover and the water and reduces evaporative cooling under the cover. A cover elevated slightly above the water surface on a frame creates a small air gap that can actually allow some evaporation even while blocking direct solar radiation. For most residential applications, a simple surface cover is sufficient and easiest to deploy and remove. The timing of cover removal in the evening is another variable worth optimizing. The ideal time to uncover the pool for nighttime evaporative cooling is shortly after sunset, when direct solar radiation has ended, but before the night temperature has dropped so low that condensation rather than evaporation becomes the dominant surface process. In most summer climates, this window begins around sunset and extends through the entire night, with maximum evaporative cooling occurring in the hours before dawn. A pool uncovered throughout the night in a dry climate with light winds will lose significantly more heat through evaporation than a pool covered overnight or a pool in still, humid air. The fountain or circulation enhancement that some passive cooling enthusiasts add to the basic cover strategy works by increasing the effective surface area of water exposed to air. A simple fountain attachment that sprays pool water into the air and allows it to fall back to the surface dramatically accelerates evaporative cooling during the evening hours. As the water droplets travel through the air, their surface area to volume ratio is enormously higher than the flat pool surface, and evaporation occurs rapidly from each droplet. The heat removed from those droplets is carried away by the surrounding air rather than being returned to the pool. This is why fountains and waterfall features in pools in desert climates are not purely decorative. They are functional cooling mechanisms. A small solar-powered fountain pump that operates during daylight hours to enhance evaporation can be purchased for under $20 and adds meaningful cooling capacity, without any ongoing electrical operating cost. The practical temperature reduction achievable through passive strategies like daytime reflective covering and nighttime evaporative exposure depends on climate conditions. But documented results from pool owners consistently show reductions of 5 to 12 degrees Fahrenheit in average pool temperature. In hot desert climates with low humidity and consistent nighttime breezes, the effect can be even more dramatic. A pool reaching 90 degrees Fahrenheit can be maintained in the high 70s to low 80s with consistent passive management. That difference is not marginal. It's between water providing genuine cooling relief and water providing almost none. This difference arrives before summer peaks, not after weeks of swimming in bathwater, deciding something has to change. The economics of this approach are striking when compared to alternatives the pool industry offers. Electric pool chillers, mechanical systems for warm pools, typically cost $2,000 to $5,000 for purchase and installation. They consume significant electricity, adding $50 to $200 monthly to household energy bills during cooling season. They also require professional maintenance and periodic component replacement. Over 10 years, Total ownership and operating costs for an electric chiller typically fall between $8,000 and $20,000. The passive cooling approach described here costs under $20 for materials if you purchase a dedicated reflective cover, under $2 if you use a basic tarp or construct a DIY cover, and essentially nothing to operate indefinitely. The performance gap between the two approaches is real, but far smaller than the cost gap suggests. An electric chiller can maintain tighter temperature control and works regardless of humidity or wind conditions. But for most residential pool owners who simply want refreshing water, the passive approach delivers satisfactory results. The cost difference is almost incomprehensible. The reason the passive approach is not what the pool industry leads with is exactly what you would expect. A $2 tarp cannot be sold at a markup that sustains a profitable retail business. A reflective cover positioned once daily generates no service revenue, no maintenance contracts, and no replacement part sales. The pool industry thrives on equipment sales, chemical sales, and service contracts. A pool owner understanding a reflective cover and open surface at night is sufficient is not purchasing a chiller. They're not paying monthly electricity surcharges, not scheduling annual maintenance, and not buying replacement components. That pool owner is, from the equipment industry's perspective, a lost revenue stream. The knowledge that creates that outcome is not what the industry has any incentive to distribute. This dynamic is not unique to the pool industry. It's a standard pattern across domains. Simple, passive, physics-based solutions compete with complex, powered, purchased product solutions for the same problem. The powered solution is almost always more controllable, consistent, and convenient, requiring less user understanding. It is also almost always more expensive, more dependent on external infrastructure, and more profitable for companies. The passive solution requires understanding how the underlying physics works and engaging with it deliberately. That requirement for understanding is framed by the industry as a burden, justifying the managed solution's cost. But the understanding, once acquired, is permanent and free. You don't need to re-understand evaporative cooling after each use, like repurchasing refrigerant or paying an electricity bill. There's also something worth reflecting on about the quality of experience a naturally cooled pool provides. A pool managed in harmony with the daily solar and temperature cycle, covered during the heat and open to the night air. It's cool in a way that connects directly to the natural environment surrounding it. The water temperature varies with the season, cools most dramatically after clear, dry nights with gentle breezes. It responds to the same atmospheric conditions that affect everything else in the outdoor environment. It is a living system, continuously exchanging energy with its surroundings according to physical laws. A pool chilled by a mechanical system is temperature controlled in a way that is disconnected from that larger environment. It maintains its set temperature regardless of weather patterns or environmental variables beyond the electricity supply. Both pools accomplish the functional objective of providing cool water to swim in, but one of them is a relationship with physics, and the other is a product. Ancient civilizations that shaded their reservoirs and built stepwells deep into the earth designed courtyards around shaded fountains. They were working with a precise and accurate understanding of thermodynamics, sophisticated enough to produce engineering solutions that, in some cases, outperformed what modern passive design achieves. The Yakchal structures that preserved ice through Persian summers, the stepwells that maintained cool water through Indian heat waves, the Roman cisterns that kept public water supplies cool through Mediterranean summers, all operated on principles any modern physicist would recognize immediately as correct applications of thermodynamic fundamentals. That knowledge was not superseded by something better. It was replaced by something that could be sold. The sun will rise tomorrow morning and deliver the same solar radiation to your pool surface. The night air will carry the same evaporative cooling capacity it always has. The physics of reflection, absorption, and evaporation that determined how ancient Persian reservoirs behaved on a July afternoon is identical to the physics that will determine what your pool temperature feels like this coming summer. Summer is coming, and this year, for the first time, you know exactly what to do before it arrives. A reflective cover, a pool surface open to the night air, and the understanding of why each of those simple things produces the result it does. That is all there is. That is all there ever needed to be. The solution was never missing. It was just never in anyone's interest to sell it to you.